Hello everyone, this is Engineer Andrew. In this video, we are going to discuss about transformer regulation. So, let us discuss some background about a transformer. What is a transformer? How does a transformer operates? A transformer operates by means of magnetic induction. As you can see from here, there are two windings on the left, which is considered as the primary, and we have here a secondary winding. It's not internally connected. However, there will be due to magnetic induction, there will be an induced voltage on the secondary winding due to the magnetic flux, right? Due to the magnetic flux generated by whenever a current is passing through a coil of winding, there will be a magnetic flux generated, right? And this magnetic flux, as you can see, it extends up to the secondary winding. So that's why there is an induced voltage across the terminals of the secondary winding. But there is no direct electrical connection between the two windings. So this is how the transformer works. A transformer is an electrical device that is designed on the basis of concept of magnetic coupling. This is what I'm talking about. It uses magnetically coupled coils to transfer energy from one circuit to another by principle of mutual inductance, right? As you can see also here, if you're familiar with the Michael Paradise, that whenever a current is passing through a coil, there will be a magnetic flux, right? That will circulate, that will be generated. As you can see here, we have an alternating current source. Of course, if we have alternating current source, our source has changing in direction, and thereby the current also here, as you can see, is changing its direction. Okay? What does transformer do? What does it do? Number one, voltage transformation. It can step up or it can step down the voltage applied to the primary, right? What does it mean? If I have here, let's say for example, I have 380 volts on the primary, and let's say the rating of transformation is 380 is to 220. What does it mean? I have 380 on the primary, and on the secondary, I will have 220 volts, right? So the voltage has been step down, right? Or let's say transformer ratio is 2:1. If I have 400 volts here, I will have 200 volts on the other side, okay? Or otherwise, if the transformer ratio is 1:2, right? 1:2, the voltage here, if I applied here, let's say 200 volts on the primary, and in the secondary, I will have 400 volts, right? So this is the transformation ratio, or we can express this in voltage ratio, okay? This is number two, isolation. So as you can see, it can isolate the circuit load from the supply, keeping the same voltage level across the secondary. So if the transformer is only being used as an isolation transformer, what does it mean? When it is isolation transformer, normally when it is used only as isolation, normally the transformer ratio are the same. Let's say 1:1, right? If I have 220 here, let's say 220 on the primary, I will have an output of 220 on the secondary. There is no transformation. Why? What is the purpose of that one? Only to isolate. To isolate, if I'm going to connect this part, let me delete this. Suppose if I am going to connect this one to my circuit here, I have a circuit. I am just isolating this circuit with the primary. This is the meaning of isolation, right? And impedance matching when you are, this is actually related to some electronics, right? When you are designing an amplifier, or sometimes your charger, most practical application, just like your charger, mobile charger, the impedance of the the output of the mobile charger must match the impedance of your phone, right? That's why it is always recommended to use an original charger. If you are using a Samsung charger, you use your original Samsung charger. Don't use the charger for Huawei, or don't use for the charger for some other cell phone, because okay, it will charge also. However, your battery might be damaged, right? On the long time, by the long use of incorrect charger, or the charger that doesn't match with your cell phone. So these are the three purposes of the transformation of transformer. Okay, now let us talk about transformer in the field of power distribution. Right, it is very, very useful in the field of power distribution. Let's start from the power generation plant. Power generation plant here. As you can see, this power generation station has an output voltage of 13,200 volts. 13,200 volts. Now, it is required for this voltage or power to be transmitted to a very long distance line, right? It's a long distance line, so it has to use a transformer, to step up. So this one is used to step up the voltage up to 345 volts, right? Okay, so now from 13,200 to 345,000 volts, so it's very high. So why do we need to increase the voltage level? Because when you increase the voltage level, the current will decrease, right? The current, because power is equal to V over I, right? So if power is constant here, if we increase V, I will be decreased. Why do we need to decrease I? Because what's the equation for power loss? Power loss is I squared R, right? If you did not reduce the I and you square it, your power loss in the transmission will be very, very high. So that's why we need to step up the voltage so that the current will reduce, reducing the losses, right, in the transmission. Okay, what about at this portion? At this portion here, now 345 volts. Now this substation here, or industrial customer, requires 69,000 volts. So it has to step down to 69,000 volts, right? And from here also, there is another distribution that requires for residential from 69,000 volts was transmitted to 13,200, right? And here, also here, another transformer, you can see here, this is 13,200 into 220. 220 is for the customer, right? Okay, so these are the transformers. So, but however, in the point of view of power distribution, they analyze the loads at different time every day. Say for example, from 12 midnight up to 4 p.m., 4 a.m., the load is very less, right? It's very less. And from 4, as the day started, right, the load has been increasing, right? Increasing, and at around 10 p.m. onwards, the load has been reduced almost same level here. This is a cycle every day, and also depends upon the season. When it is summer season, when it is a cold season, so of course the usage of air conditions also a factor, right? The load on the large power transformer vary from small value in early hours on the morning to a very high value during heavy peak or maximum industrial commercial activity. Where is the peak load here? Here at this point, this one, right? This is the heavy. So it varies. What is the effect of that varying load to the transformer? As you can see here, these loads here being catered, all of them, these loads here being catered from the power source by this transformer, right? Or if you go into this transformer point of view, it's carrying all these loads, right? So what is the voltage regulation here? We had to determine for today. We will know what is the voltage regulation here. What's the voltage regulation here, or this transformer? What's the transformer's regulation here? So this is how the voltage regulation is being applied in the power distribution system. Okay? Now, before we proceed with our discussion, let us have a revision. Maybe some of you had already forgotten the phasor analysis of a and the power factor of the RLC element, right? So here, for a purely resistive load, as you can see here, they are connected in series. This is my example only. I have all the currents are the same. Okay, all the currents are the same. So the voltage across the resistor is VI minus R, and the phasor diagram is that the current and voltage are in phase with each other. Okay, in phase with each other. Now, what about the inductor, which is this one? For the inductor, we can say that the current is lagging from the voltage by an angle of 90 degrees, right? The current is lagging from the voltage by an angle of 90 degrees. And in the case of the capacitor, the current is leading the voltage by an angle of 90 degrees because our phase rotation is counterclockwise, right? This one, this is the analysis. Just like in your first quadrant, second quadrant, third quadrant, right? In your coordinate system, fourth quadrant, so the rotation is counterclockwise. So this one here, the current is leading the voltage in case of capacitor by 90 degrees. Well, we can say the current is leading. So if you can still remember, power factor of the capacitor is leading. Power factor is leading, right? And here the power factor is lagging if it is inductive load, and power factor for the purely resistive load is unity, is equal to 1, right? Is equal to 1. Okay? Now, I have just for better analysis also, I had assembled a combination, the circuit. Let's say I connected a purely resistive load using our lab volt simulation, and to show to you the phasor, right? I have here a 1100 ohm load connected to a voltage source, and so I put it in maximum. It means line to neutral. What will be the line to neutral voltage here? 220 volts, right? From 4 to N, right? I'm measuring that. So when I click the phasor, I want to know the phasor. As you can see here, the voltage and the current are in phase with each other. So to summarize, the current is in phase with the voltage source. The phase angle theta is 0 for a purely resistive load. The power factor is equal to cosine theta, which is equal to 1, right? Or power factor is equal to 1. This is for what? Purely resistive load. As you can see here, I put only purely resistive load. Pure resistive load. Now, if I combine this resistive load with an inductive load, right? An inductive load and simulate the circuit, the current will be lagging, right? The power factor will be lagging. As you can see here, this is the current phase, this is the current phase, this is the voltage phase. So in here, this combination, we can see this is lagging, right? The current is lagging the voltage by some angle, right? But this angle I can calculate, actually here is 1100, 1100. The theta here is arctangent 1100 over 1100. The arctangent 1, or it's equal to minus 45 degrees, right? This will be my phase angle here. Okay? This is also a review of our power factor. If I put a capacitor, look at what happened to the current. It becomes leading, right? And also I use the same value 1100, 1100, and I can calculate the theta here is equal to 45 degrees. Okay? So the current is leading. The theta is arctangent x of c over r. It will give me, in this case, 45 degrees. The power factor is leading. The cosine and is equal to cosine theta. The power factor, of course, is always less than 1, right? When it is equal to 1, that means purely resistive load. And for the inductive load, again, current is lagging. Power factor theta, XL over XR. And the power factor is lagging. It's also less than 1. Okay? Now, these things you need to remember when we discuss later on about how we analyze the voltage regulation of because the load, right? The load will affect the voltage regulation of the transformer. So, we have to remember what are the characteristic and behavior of the load. So, now let's go to the next slide. here it is said that the transformer secondary voltage depends upon what? Leakage impedances on the primary and secondary. So there will be some losses. There will be some leakage impedances. Number two is the loading condition or the load that we are going to connect, where it is heavy load, high load, or very light only. What is the effect on that on the voltage regulation? And the power factor of the load, right? The power factor of the load and the type of loading, leading, lagging, and unity, right? So these are the factors that affect the transformer and the secondary voltage. Now, it is very important to know how the transformer secondary voltage behave under different loading condition. This is the purpose of voltage regulation. In order to evaluate or consider the changing or to control transformer output voltage, this behavior is voltage regulation, right? It's important for us to know that the effect of the different loading conditions in the secondary, so that we can control. We can say that okay, this load will give a bad effect on the secondary of the transformer, so we can control, we can minimize, or we can adjust something in our load, right? Or when we are selecting, when we have a load, when we are selecting the transformer, yeah, right? This is the transformer. We have to connect a load. We need to, before we buy a transformer, normally, before we buy we analyze the transformer, right? Especially guys, if you are buying a very large transformer, right? Buying a very small transformer is not the same as buying a very large transformer. Just like in power system. In buying a very large transformer, you need to evaluate everything and you need to do some calculations. So you can decide the best suitable capacity of the transformer that you're going to use. For a small transformer, although we also need to calculate, but it's not that much critical as compared to a very large transformer. And of course, large transformers are expensive. You don't just buy a transformer and by trial and error, right? You must have some calculation. That's why they will hire an electrical engineer. Okay, now what is voltage regulation? Again, voltage regulation is the measure of how much the transformer terminal is going to change when fully loaded compared to the case when there is no load. So we are comparing B no load and also B full load, right? Okay, this is some example of transformer here, the bottom. Now, okay, as we mentioned earlier, the leakage impedances also affect the transformer secondary voltage. So let us try to discuss what are those leakage impedances. So in the transformer, there is what you call iron loss and core losses. And core losses has been divided into two. It can be hysteresis loss. What is that hysteresis loss? It is the loss due to a reversal of magnetizing in the transformer. As you can see here, there is a reversal of magnetizing, right? There is a loss because of that. And also, letter B is the eddy current loss in the transformer. What is that eddy current loss? Some parts of this flux gets linked with the other conducting parts like steel, core, iron, body, or the transformer. Of course, the transformer has some case, some nut bolt there, but there is a circulating magnetism. So it can also be generated as heat. So this is called eddy current loss. So this loss are the core loss or iron loss. And we also have another loss, which is copper loss, which is due to the copper due to the ohmic resistance of the transformer, right? So that we have a winding. So it has some length. Then length, we have the resistance with respect to length, and also since an inductor, it also has this is a coil. It also has an inductive effect, right? Inductive effect. So aside from the resistance, due to the cross-sectional area, length or cross-sectional area, there is also an inductance in the transformer, right? Induction. So These are the losses that affects what? The secondary voltage. Okay? Now, this transformer, now considering the losses, I can now represent this transformer in an schematic circuit. So this here is the core losses. This is the core losses here, right? Core losses, and this part is the copper loss in the primary side, and this is also the copper loss in the secondary side, right? This is the exact schematic circuit of a transformer, right? We're going to use this circuit to analyze the voltage regulation. It means to say that with this circuit, when we connect a load here, whether current is whether the load is lagging, whether the load is leading or unity power factor, it has effect on the secondary voltage, right? We are always we want to know the effect of these loads into secondary voltage because we are specifying the transformer capacity, rated voltage. Okay. Now, before we proceed, having this schematic, knowing this schematic equivalent of the transformer, and before we start in the voltage regulation analysis, this circuit can be represented by this circuit. This is called reflected impedance. By means of reflected impedance procedure, I can reflect these loads here in the primary. I can transfer it to the other side by means of impedance reflection. So what are we going to do? In the transformer, we have what you call the voltage ratio or the current ratio, which is we call it A, BP over BS is also equal to IS over IP, or NP, or number of turns in primary, and number of turns in the secondary. These are all equal to A. What is the importance of A here? So meaning to say, the impedance can be reflected, the set reflected impedance of primary, let's say this reflection, this impedance here, I want to reflect it to the secondary, that I can use this equation, set reflection is equal to set of the primary over A squared, right? Set of the primary over A squared. Now, let us focus on this circuit. I want to reflect these impedances of the primary into the secondary. Now, this part here, this circuit here is already the secondary. Now, I want to reflect this XM and RC into the secondary, so I had to divide by A squared. So from here, RC over A squared, right? We have RC here, and XM over A squared. So they are still parallel. Now I am reflecting this to the secondary side. What about the resistance? The copper loss. We have here RP. We have also we have RP here, we have R primary, we have R secondary. So I need to combine these two, RP and RS. So I can call it R equivalent is equal to RP over A squared plus RS. Okay? And X equivalent is equal to XP over A squared plus XS. So, and now I can put this value here, X equivalent and R equivalent. So I now have a simplified circuit wherein I want to know what is the effect, right? Our main objective is to know the effect of the load at the secondary. That's why I brought this load, these parameters into the secondary so that we can directly examine the behavior of the circuit, secondary circuit that is connected to the load, right? This is where we connect the load in the secondary. Okay? Of course, this current also, primary current is equal to AIP, right? AIP, because A is equal to IS over IP, therefore I'm calculating IS, the current here, is equal to AIP. Okay? Now this is the equivalent. Now it's not on our topic that we had to, just for your information also, in the previous slide, I transfer this parameters to the secondary, right? But also these secondary parameters can also be transferred to the, or can also be reflected to the primary, right? We are going to use the same pattern. As you can see here, the simplified, if I reflect this the secondary impedances into primary, it will becomes, I have here now, I combine RP and RS. So R equivalent is equal to A squared RS. So and plus RP. So it will be A squared. If you are reflecting to the other side, to the primary, it should be A squared RS. It's not RS over A squared when you are converting. So it's wrong. So it should be A squared to RS. That is the difference. Okay, we have REQ, XEQ, and we have this the same, and now we have reflected it on the other side. But we are not going to use this in our voltage regulation analysis. We are going to use what? The first one, this one. Okay, because we are talking about the secondary. So now, the effect of the excitation branch on the transformer voltage regulation is minimal. What does it mean? The effect of this and this is minimal, right? So we can ignore it. And then only the series impedances can be considered in the analysis. So we can ignore it. We can have simplified circuit, right? And the easiest way to determine the effect of the current phase angle and the transformer voltage regulation is by examine the phasor, right? Let us try to examine the phasor here. So we will use, in our analysis, in our phasor, we are going to use BS as a reference, right? And if we use BS as a reference, what will be this BA over P? What will be this one here? Here we have a voltage, right? BREQ. And here we have BXEQ, right? We can obtain here a KVL, if you still remember the Kirchhoff's voltage law, that the voltage in the loop, inside the loop, will be equal to 0, right? Okay, let's go to the next slide. For transformer regulation, let us now analyze the transformer voltage regulation for different power factor of the load. So, lagging power factor. When the power factor is lagging, right? So, when the power factor is lagging, as I've said, I'm going to use BS as a reference. So, this is my BS, angle 0. When the power factor is lagging with this voltage, meaning to say, I have shown you, the current will be lagging. So, what will be this phasor? This phasor, when it is lagging, it will be in this direction, right? IS. And IS, right, you can see here, what's the relationship between the voltage, B of the resistor, and the current? They are in phase. So this is a resistor. It means to say the phase also of BR is the same. So since we are doing phasor addition, I can reflect this current phasor in this point here, where I can represent this as voltage, right, is equal to BREQ, right? This is IS multiplied by REQ, this will be the voltage, and plus what is this voltage? This will, if I took the KVL here, this voltage plus this voltage plus this voltage will be equal to this voltage, right? This is the considered as a source. So BS plus BREQ plus the voltage of XEQ, we have 90 degrees here, right? Because you know the current is going here, so it will be, the current is lagging. So we have now B of XEQ, this portion, this yellow line. So when you add all of the voltages, it will be equal to BP over A, which is BP over A. This we can consider as B. This point here is equal to our B no load, but because at this point, the load is not yet connected. This is the B no load, right? BP over A. So as you can see from here, if you can compare what is the voltage across secondary, the voltage of secondary is smaller than the BP over A, or the B no load. So we can say that when the load is lagging, E no load is greater than E full load. Okay? And the voltage regulation is greater than 0. Why greater than 0? I will show you later the equation of a voltage regulation. The voltage regulation is greater than 0, meaning it's a positive value, right? It's a positive value. Now, let's talk about voltage regulation. Voltage regulation equation is BP over A, which is our E no load, minus BS full load over BS full load. multiplied by 100%. Very, very simple equation. Or we can say E no load minus E full load over E full load minus over E full load multiplied by 100%. This is the voltage regulation. So for if the voltage, if the load is lagging, right? If the load is lagging, we summarize E no load is greater than E full load. So this portion of the equation will be positive. You have a positive voltage regulation. Okay? Now, what about when it is unity? Right? When it is unity, what will happen to the phasor? When it is unity, we can just analyze. This is our BS up to here. And if it is unity, if the load is unity, so that means REQ, what is the current? If it is unity, here, right? Here, right? So this will be the voltage, REQIS, and this will be the BXEQ. This will be this BREQ. So adding this together, we will have now, this is E no load, right? E no load. So, but as you can see here, the E no load here is a little bit shorter than the earlier voltage here, which is longer, right? So we can say that still, for purely resistive load, E no load is still greater than E full load, right? And the voltage regulation greater than 0, also a positive value, right? Voltage regulation is greater than 0, BP over A, or the E no load is greater than BS. And as you can see here, from this equation here, this is from KBL. We derived this equation from KBL, right? Let us take the KBL here, right? Minus BP over A plus REQRS IS plus JXEXIS plus BS, right? Will be equal to 0. Solving for BP over A or E no load, we have all the summation of voltages. Summation of the voltages. Okay? This is from Kirchhoff KVL. Now, what will happen now if we have a leading power factor? Leading power factor. So, let us now again focus on BS. This is our BS. This is our reference. If it is leading, where is the current? The current is somewhere here. Leading, right? Leading. So, we can reflect here this voltage of VREQ. So, VREQ. Right? And from here, we can add now the BXEQ here, right? And this will be now BP over A, or this is the E no load. So what did you notice? What did you notice? When the load has a leading power factor, E no load is less than E full load. So if it is less than E full load, what will happen to this part of the equation? It will become negative. So we have a negative voltage regulation. Okay? We have a negative voltage regulation. Of course, the voltages here are being described by Kirchhoff's voltage law, right? From this, summation of voltage in a closed loop is equal to 0. Okay? So, also, when you are talking about the transformer voltage regulation, we cannot avoid talking about the efficiency of the transformer. It's just P out over P in, where your P in is only the output plus losses. And I discussed to you the losses. What are the losses? Due to the copper loss and core loss, right? This will be your efficiency. So P out over P in only. What is your P in? P in is the summation of P out plus P loss. So this is your P in. Very simple. This is the efficiency of the transformer. Now to summarize our discussion, voltage regulation is to measure how much the transformer terminal voltage is going to change when fully loaded compared to the case when there is no load, not loaded. So this is the equation, E no load minus E full load over E full load times 100%. And we define E no load and E full load. That the smaller the voltage regulation, the smaller the secondary voltage variation with the with load, the better the voltage regulation. Again, the smaller the voltage regulation, the smaller the secondary voltage variation with load, the better the voltage regulation. So if your voltage regulation is smaller, there is a slight change in the BS, so we can consider it as a better, the transformer has a better performance. Now, voltage regulation may be positive or negative depending on the type of connected load. And also, efficiency, P out over P in. Okay?